Today's speaker is Ignacio Sepulveda. He is originally from Chile. He did his bachelor's degree there in civil engineering. At the time, he was interested in extraction of tidal energy. He went to Federico Santa Maria University in Chile. But then he came to the US and did a master's and PhD in civil engineering at Cornell University and started working on the solutions to tsunamis and geohazards and the characterization of uncertainty. He continued to work on geohazards as a postdoc at Scripps, working with Jennifer Haase, and recently finished there and started an assistant professor job at San Diego State University. And so he's going to show work that he's done over the years on tsunami modeling. He's worked a lot on practical studies in Chile, but also in Tonga and Indonesia. The title of his talk will be Compound and Cascading Processes Shaping Tsunami Responses, a New Era of Multidisciplinary Research. Thank you, Ignacio.
Thank you very much, Carl. Wow, very, very cool bio. Actually, better than the one I have. I will ask you for that. So thank you everyone for coming. It's a real pleasure to be here in Austin. Actually, I wanted to come here for a long time, basically because in my PhD research, I was reading the research, for example, made by Dr. John Goff, and actually we had a meeting a couple of minutes ago, and also I have seen the quality of the students that have arrived there to Scripps, and I have learned a lot for the people. So it is a real pleasure to be here and to share with you this research I have done in the past few years. So just a brief introduction of who I am. Basically, I was born in Valdivia, in southern Chile, in 1984, actually. I born 24 years after the great earthquake of 1960 struck the coast of southern Chile, the greatest earthquake recorded by our technology. Okay, so I grew up looking at the history of Valdivia and what happened because of the earthquake. Of course, the earthquake was terrible. The ground shaking destroyed all the city, but certainly, probably the most remarkable effects or cascading effects of that earthquake were related with water-related hazards. Two examples are the big tsunami that hit Valdivia, and actually here you can see a big picture of a big steel factory next to the coast, which was completely washed out because of the tsunami. Actually, this ship jumped over the factory. This was the final destination. The coast is at the other side. And also, upstream Valdivia is crossed by a very beautiful river. But upstream that river, we had what we call the lake quake. Basically, what happened is that at the exit of the lake, you had a lot of landslide because of the ground shaking that created a natural dam. And basically, that dam, you had the threat that you will have a dam break and you will destroy Valdivia. So in addition to the big tsunami, you had the big problem that you have a lake quake, and you need to try to solve that issue. How we solve it? With hand, shovel, and using hydraulic engineers to try to predict how you had to create a river in order to relieve the head from that lake. And finally, you save the city. So as you can see, I always have grown up is inspired by this work from geoscientists and engineers trying to deal with water hazards. So, there you are. So of course, I started working as an engineer in Chile. I did my civil engineering. Actually, this is exactly the same place where we had the lake quake. Here we were doing some studies because an energy company wanted to do a dam there. It was a bad idea. At the end, they suspended the project. They canceled the project. But I was there because we wanted to study the risk of landslide tsunamis created because of the same landslide, but now on the lake created by this artificial dam. So basically, I had to study what happened with the landslide tsunamis or the future landslide tsunamis that you may have. At the end, the project was canceled. Also, I have done a lot of work related with tsunami hazard assessment, especially after the 2010 in Chile. This is a natural gas port in central Chile, one of the most important ports in Chile. And of course, we needed to assess what is the tsunami hazard. So the question is why we are so aware, so concerned about tsunamis, why we should study tsunamis. Now we have climate change, we have problems with social justice, we have many problems, and societies are dealing with a lot of issues. And probably tsunami is the last thing you will start to be concerned here in the US. But as a matter of fact, well, you are right in the sense that, actually the death toll here in the US is pretty small. This is the last century, the death toll of the tsunamis in US territory of the last century, and you can see how actually the death toll is very small for the last century. But actually, it's very interesting that the UN, the United Nations, is saying that actually tsunamis account for the 10% of the total economic losses you may have in the world in the past two decades, in the past 20 years. Basically, because you have the Sumatra earthquake and you have the Japan earthquake. So why this is a 10%? Why is so high, considering that this is a hazard that is actually not so hazardous? Well, you have probably two very important explanations. First of all, you need to understand that 40% of the world population live next to the coast. So we really need to be aware about coastal hazards. And second, there is a matter of probability. If I ask you right now, you will say that an event like a tsunami, a big tsunami like the Japan or the Sumatra, which happened with a recurrence of the order of 1,000 years, probably for you, you will say this is very unlikely, right? 1,000 years is a lot. But actually, if you just apply a Poisson model, the typical model we use in order to understand frequency analysis of extreme events, and you put there your lifetime, which is for the US average US person is 78.2 years, that is what you will live. If you put those parameters into the formula, you will realize that actually your probability to experience a 1,000 recurrence hazard event is actually a probability of 7.6%. That is high. Maybe you say, well, how I compare this thing? Well, very easy. Go to internet, check what happened with the probability to be diagnosed with cancer in your lifetime, and you will see that actually the probabilities are very close. Now, also, you have other problems. When you have a tsunami, the economic losses are huge. Maybe this thing will have a very low recurrence, but when it happens, and if you don't do anything, the money or the infrastructure you will lose, it will be huge, and you will create an impact on your society, on your government. So therefore, probably in the last century, it was not so recurrent, it was not so interesting, but certainly is something you need to be aware of, and you need to study, and we need to understand the process in order to reduce the risk to have life losses and economic losses. Okay, so the machine or how this research or the application work for the tsunami science or tsunami hazard assessment is basically, first of all, you need a problem. And that problem is basically you have infrastructure, and that infrastructure is exposed to hazards, to coastal hazards. This can be tsunamis or any other coastal hazard that you may imagine. First of all, what we need to do is to apply a lot of science, tsunami science or coastal hazard science, in order to first be very good collecting observations and data from the natural event. We need to try to derive modeling tools in order to reproduce and in order to understand the relation behind these measurements that we have or the impacts we have. And finally, also, and recently, I would say in the past few years, we really need to acknowledge that we have uncertainty in our predictions of the hazard. We have an uncertainty in the occurrence of the event in the future, and also we have an uncertainty in the intensity of that hazard. So certainly we need to acknowledge that we have an uncertainty. Now, once we get some maturity on this aspect, you can start working with some applications for engineering. We can start defining a most credible scenario in order to create a worst case scenario, so we can use that for design. We can even go more sophisticated and try to establish probabilistic tsunami hazard assessment tools in which we can include uncertainty of the occurrence in the future and the intensity of the tsunami in order to provide a probability for design. And also we can even move much forward and try to build fragility curves in which the natural hazard is connected with the behavior of the infrastructure at the coast, and you can come up with a probability of failure of your infrastructure in terms of structure and operation. Now, once you have all these tools, you can come up with three alternatives. You can reduce the exposure of your infrastructure by moving to somewhere else. You can reduce the vulnerability by, for example, building a big wall, anti-tsunami wall, or simply, if you cannot do anything with respect to the hazard and the vulnerability, at least try to make or design some plans in order to reduce the risk of human losses. For example, defining evacuation plans. Now, in this presentation, this is like the, I would say, what we are trying to do every day. And of course, this is not a work that is ended. We are constantly improving these topics. But I want to show you two components which are actually very important, I believe. One is this special cascading phenomena that are producing tsunamis. In 2018, we had a tsunami in Palu in Indonesia. And basically that tsunami was super interesting because it was huge, but the earthquake that created that tsunami was a strike slip earthquake. And actually the intensity was very small. And anyway, we were having a big tsunami, which is very rare. So what happened there? I say that it could be landslide tsunami. Other people say that it was a special tsunamigenic mechanism related with super shear earthquakes, because that was a super shear earthquake. And also last year, we had the big surprise that we had an explosive volcanic eruption, similar to what we had in 1883 in Krakatoa, now in Tonga. And that big explosion created a tsunami. The interesting thing is that the tsunami was not only created in the Pacific Ocean, in the basin where you have placed that volcano, but also in the Atlantic and in the Caribbean. So that was a mind-blowing. I was saying, oh my God, what's going on here? Everything is wrong. So certainly, I would say that one of the new dimensions that we need to develop in tsunami science is this research on non-conventional tsunami genesis. It's not just earthquake. I know that we have a lot of problems related with how we can predict and we can characterize an earthquake tsunami, but now we are also have to add more sources for tsunamis. And this is a big problem. And it's very exciting because we have a lot of research on that topic. And another very important thing that actually I will start my presentation is related with compound processes. When you have a tsunami at the coast, that tsunami is combined with other things. It's not just the tsunami. For years and years, we have been working with our tsunami models, and we just have put the tsunami in the mean sea level, and everybody is happy, and you receive your check from the client where you are doing the study. However, after the 2010, for example, in Chile, we observed after post-tsunami surveys that the tide played a very important role in the behavior of the tsunami. The tide was low at the moment of the earthquake in 2010 in front of central Chile. And actually the first wave was not so intense. Why? Because the tide was very low, and actually was the minimum low because we were in the middle of a springtime. So actually the earthquake happened in the best time. However, once the hours started to pass on, we started to see effects. Actually, the earthquake happened at 3:30 a.m., but you can see the videos of the tsunami of 2010. You can see waves at 8 a.m., at 7 a.m. Basically, because you had all this complex behavior or combination between tides and tsunamis. And also because you had edge waves and you have some resonances which took some time to bring. But the important point is that you have compound processes. And if you want to do a hazard of the tsunami, you need to acknowledge that you have a combination and you have compound processes happening there. Of course, the new interest that everybody is thinking about, and this is the reason of one of the papers, is related with the sea level rise. How you will include sea level rise in your estimation of probability for the life of your projects. For example, you have a big important port which need to last 50 years. How the risk or how the probability of the hazard intensity will behave because you have now to add a sea level rise. And this is what we will see now. Okay, so we will start with this compound process idea. Then we will talk a little bit about volcanic tsunamis at the end. So let's start here with the first slide. So what I was telling you right now is that you may have tsunamis. And tsunamis, you will have this. Sorry, there you are. So you will have some waves coming with different intensities every time you have a tsunami, or you have a source that happens and it will create a tsunami. So here I'm showing you like 6 events. Let's imagine that you have 6 earthquakes happening in the future. The problem is that, first of all, you will have tides. So tides will change the sea level at the moment of that the tsunami arrives to the coast. But also, while the time is passing and you have decades, while your infrastructure is working, you will start to notice that sea level rise will kick out, and you will start to notice the sea level rise. What happens with sea level rise? Of course, will help the tsunami to reach higher land, and then we are in trouble, right? Okay, so basically, you can see here an evolution. Here you can see an evolution of the sea level. And in blue lines here, you can see what is the value of the tide. Sometimes you will have the bad luck to have a high tide. Sometimes you will have the good luck to have a low tide, like 2010, and so on. But the question is how we can take this formulation that we have used for 30 years, which is related with the probabilistic tsunami hazard assessment, which is, by the way, the same as the probabilistic seismic hazard assessment coming from Aline Corner from MIT. And the idea is to think, okay, how we can take that formula and try to adapt it to acknowledge the fact that we have a non-stationary process combining with the tsunami, how we will deal with that. Okay, to do that, of course, we have to go a little bit to the fundamentals and try to understand what happens. So the Poisson process that we typically use for probabilistic seismic and tsunami hazard assessment has this form, in which you have an exponential. This is the probability to not have a tsunami during a certain amount of time, the lifetime of your project, for example, that is capital T, for example, 50 years. And lambda is basically the average recurrence of your hazard, how frequent you have a tsunami. And of course, we have a summation because we can have different type of hazard, sources of hazard. Now, because we are dealing with tsunami, we know that tsunamis are very sensitive to the characteristic of the tsunamigenic source. For example, in the earthquake, we can notice that tsunamis are very sensitive to the slip distribution. Therefore, if you say that you have an average recurrence rate of a magnitude 9 every 400 years, you know that if you have 2 earthquakes, you know that both will not do the same tsunami. So you have an uncertainty there. And that uncertainty has to be included with a very innocent parameter here, which is called the P, the conditional probability P. So basically, this is a probability distribution, assuming that all these driving variables defining the shape of the tsunami are random. Assuming that, you can create a distribution saying that what is the probability to have a tsunami with an intensity of, for example, a height of 2 meters, given that you have an earthquake of magnitude 9. That is a conditional probability. Okay? So if you have that probability, now you can modify the formula that we have here originally, and you can get the probability to not have a tsunami with that intensity or exceeding that intensity in a given amount of time, in a capital T, which is the lifetime of your project. How you get that P? You can use Monte Carlo simulation. You can use more sophisticated model like a stochastic reduced order model, which is what I use. You can even use machine learning, I would say. You can use many, many ways to try to find that P. But of course, it will require you to do a lot of tsunami simulations. And most of the time consuming part of the probabilistic tsunami hazard assessment is running simulations to get that P. So finally, from this formula, you can get the probability of not having a tsunami exceeding a certain intensity. Okay, so this is the formula. This is what we have used for 20, 30 years. But now the question is, okay, so now how we can include a non-stationary process on that formula? What we should do? don't try to change this too much, because of course we will need to re-educate all the engineers doing this kind of job, but they need to be familiar with something similar to it. So in order to do that, we will try to preserve the Poisson process, but we will try to work with an inhomogeneous Poisson process. So going back to the derivation of the Poisson, basically you know that this equality or this approximation holds for differential of times. So if we are here today, we will see that this formula holds. But now let's imagine that we are in the next century. In the next century, you will have a certain sea level. That sea level, because it's higher now, because of sea level rise, the probability that exceed a certain tsunami intensity will increase, because basically the sea level rise is helping you to reach higher land. And therefore, the probability to reach a certain intensity is getting bigger. Because of that, this equality holds. And of course, now if we go back to the integration of this formula, we can discover that we have almost the same, but the only difference is that now you have a temporal integral there. So the formula is almost the same like that, but now you are acknowledging that you have some variables changing in time. Basically, an integral Basically, an integral will be a multiplication of exponential, and because a summation of a multiplication of exponential is equal to the summation of the exponents, you can come out to the integral form. You see? Okay, very good. But we have a problem. How we will get that integral, considering that we require a lot of time to determine the value of P for a given time. So now we have a numerical problem or a practical problem. How you will solve, at least as an approximation, that integral. Very easy. We can apply a surrogate model. So what does the surrogate model do? Basically here, what you can see is three curves. These three curves are actually the cumulative distribution of the value of P. Basically here you have a probability, for example, for exceeding a certain value HC given a magnitude 9, and you will have different numbers and different probabilities for different numbers. With a surrogate model, what we will do is create tsunami simulation in which we are adding a specific and a constant offset into the numerical model. For example, we will simulate tsunami for 100 years. That means that to the sea level rise, to the sea level that we have today, we will need to add, I don't know, 1.5 meters. And we will start run tsunami thinking that we are in 21, 24, in 100 years more. And we will do this for 100 years. We will do this, for example, for 50 years, and we will have three different curves corresponding to different states, which we call the collocation epochs. And in order to get the value of P for any time, you just do a linear interpolation. This is what a surrogate model used to do. Okay, so if we run here the video, you can see the time, different sea level rise for different years, and you can see how the curve P is moving around. So now that you have an estimation of the value of P for the value of P for any of these intensities, you can now use this surrogate model to put it inside your integral. You can solve it and you have the job done. And for this, you need 3 times the time you require to do a classic probabilistic tsunami hazard assessment, but that is super doable. Okay, that is the first problem. The second problem is related with tides. The variation with tides change in a time length much faster than what you think about the lifetime of a project or the cycles of an earthquake or of a tsunami-genic earthquake, right? Tides change. You have too lows or too high in one day. So it's very fast. So instead of including the tides inside the integral of the non-stationary probabilistic tsunami hazard assessment, what we can do is account the tide as an additional random number. Of course, supported by a couple of assumptions, which actually are very strong, and later I will show you where we need to modify this. But if the tide is a random number, actually you can go to the repository from the University of Hawaii, for example. You can get data for more than 18 years, more than the Meton cycle. You can take a statistic of the sea level in a certain station, for example, Hong Kong. You can remove the sea level rise. You need to get the detrended, so you don't account for the sea level rise twice, and you can get a distribution. This distribution is basically the value of F eta. So then, using the same collocation epochs of the surrogate model, you can say, give me the P, given that you have a certain value of eta. Using exactly the same collocation points that you used before, and you can now draw a formula to include sea level rise as a non-stationary process and the tide, which is actually very important because it's comparable to sea level rise in 1 center. We're talking about order of meters. Okay, as an application, I was working in the South China Sea. Why South China Sea? Because my advisor, we could find a lot of data here, and it was a very nice natural lab in order to do application on these topics. We are working with tsunamis generating in the Manila Subduction Zone. What we are using is some earthquake recurrence that we can obtain from a segmentation we did to the Manila Subduction Zone. Here I receive a lot of help from the people from the Air Observatory of Singapore. Lin Lin, for example, who is a colleague, Lin Lin Li, who is a colleague who worked at EOS, and now she's working in China. She's a faculty in China. She helped me a lot. Actually, she started with the first probabilistic tsunami hazard assessment in the South China Sea. And here we tested a random field model that I created for my PhD in order to create synthetic earthquakes. And using the classic probabilistic tsunami hazard assessment formulation, I draw 6 curves, 3 for Kaohsiung in Taiwan and 3 for Hong Kong in China. This is the classic method. Then I use my formula in order to include tides, which is the red curve. Then I include sea level rise only, which is the black curve, and then the red curve combining sea level rise and tides. And I started to evaluate the impact of both phenomena compounding to the tsunami. And what you can see is actually the tide, because the tide range is actually not so high in Hong Kong and Kaohsiung, actually is not doing a big deal to the tsunami result. Here you have a relative difference. Basically, it's the same plot, but here I'm dividing with the segmented curve, which is the classic one. And you can see that actually the sea level rise is actually generating a great impact into the probabilities that a certain intensity is exceeded in the time. Okay, another very interesting thing is that I took these curves, and instead of represent the cumulative density, the cumulative distribution, I plotted the density function, which is basically the derivative of the cumulative distribution. And you can see here is very clear what is the effect of the sea level rise and tides. So here in blue, you have only tides. You can see that the tides is spreading the probability of the tsunami hazard in terms of distribution. You are getting low probabilities, but you are spreading to higher values of tsunami. For the case of the sea level rise, you have a spread. Here is the, you can see the black one. You can see that you have a spread, but also you have a shift towards higher values. This is how this behaves. This is how you are impacting your values of the tsunami. And this is more illustrative. It's actually, this is the probability to flood regions in Hong Kong for an exposure time or a project lifetime of 100 years. The first one is the classic method. The second is the method with sea level rise. Here you have only tides, and here you have sea level rise and tides. And you can compare what you had with the classic method and what you have with the new method with tides and sea level rise, and you can see that the impact is actually very strong. I have to warn you here that for South China Sea, these effects are very important. Why? Because tsunamis actually are very small. Probably if you apply this method in Chile or in Japan, where the tsunamis are super huge, tsunami easily is 15 meters, 20 meters, probably the effect of the tides and the sea level rise probably is not so important. In these places where you have middle magnitudes of tsunami, it's very important. In California coast, probably it's very important. But in Japan, in Chile, probably it's a secondary thing. Okay, but anyway, you need to evaluate it because sometimes you can have the bad news. This is the formulation, by the way. So you can have the bad news that actually tides are very strong in the area where you are assessing tsunamis. This is Chacao Channel, southern Chile, in which in spring tides you can reach velocities faster than 5 meters per second, easily. And actually, I was working on this side because now Chile is building a suspended bridge in this. So the problem is that sometimes tides are huge, and you need to acknowledge that in your tsunami hazard assessment, and you need to include it. Okay, that is related with compound hazard. Now I want to talk more about the mechanisms to generate tsunamis. And since I started my postdoctoral scripts, I have had the bad luck that all the new tsunamis have been doing a completely different thing of what I have learned in the past 10 years. So I have had to do a new or a second PhD program learning about tsunamis, which is very exciting, by the way. We are here to learn and to explore, so it's not a bad thing. Okay, so January 15, a year ago, I woke up very early on Saturday because a friend was calling me, hey, we have a tsunami. What type of tsunami? No, we had a volcanic eruption, and I hear about the volcanic eruption. I say, come on, we're in California, what will happen? So I started to sleep again, 7 a.m. Saturday. And then I woke up at 9, and we started to see the huge tsunami waves and the huge current, well, not huge, but moderate and important, happening in California. For example, here is Santa Cruz, where we got some flood. And also I was receiving phone calls from my family in Chile. Ignacio, what is going on in Chile? And I didn't know what was happening. And actually my parents took a picture of the beach and showing me the low level of the trough of the tsunami arriving to the beach. And it was pretty scary. So, of course, this is a natural practice. I started to do some traditional tsunami models in order to see if I could reproduce something. And that reproduction was fine as long as I was putting a huge initial condition at the place of the volcano. So basically putting a huge bump as an initial condition in the volcano, you would be able to reproduce tsunamis in the California. The bad news is that I started to receive news from Tonga, and actually the Tonga Island was there. It doesn't disappear. In order to have a big initial condition, you had to destroy completely Tonga Island. And it was there. There was damage, there was a tsunami, but it was there. It was something not strong, not in order to cross the ocean. So I started to feel very uncomfortable with this. And then we started to receive the news that actually in the Atlantic Ocean, people were perceiving and observing with instruments tsunamis of 1 meter of amplitude. And in Puerto Rico, in Mona Island, 20 centimeters. And I was saying, oh my God, how is that possible that the tsunami was crossing the Americas? Now tsunamis are crossing continents. How is that possible? So then we started the journey. Basically, here I have to acknowledge 2 great collaborators, Matias Carvajal from Chile, he's a professor in Chile, and Duncan Agnew, a professor from Scripps. Nothing to say about these 2 guys, super cool. I have learned a lot from these 2 guys. Well, but let me show you the chronology. January 16, Stefan Greeley from Rhode Island, a professor in coastal engineering, telling us that probably atmospheric pressure waves are creating tsunamis. And I say, how is that possible? This is a minor thing. Impossible. But anyway, we started to think, oh, maybe we have problems because the measurements are not fitting with the traditional model. January 17, we downloaded all the dark buoys data. And we started to see that actually the great waves are actually having sense with what we having from a traditional model with a source, with a water source coming from the volcano. But before that, we were getting a lot of noise, a lot of waves, which was not noise, was actually a physical thing. And that thing was tsunamis and pressure created by a huge atmospheric wave traveling over the globe and traveling many times. January 20, we learned that waves at Tonga were important, but not very high. That is what I was telling you before. This was consistent with the traditional way in which a tsunami have a big initial condition and start to propagate in the ocean. So there was no way. We were also analyzing, that is what I was telling you, and we found that there were significant tsunamis in the Atlantic. Finally, in February 4, Vasily Titov from PEMEL at NOAA, he finally could develop with the collaborators a couple tsunami model in which they were putting a simulation of one of the modes of the gravity acoustic wave, which is the land wave, which is traveling with a velocity of 320 meters per second, more or less. And he was coupling that with the tsunami, and he was capturing at least the shape of the wave. So, oh my God, he found it. So since then, we have been working, trying to model this event. So the first paper we wrote with Matthias, this was the first day, the first couple of days working with this tsunami, which was almost like a forensic work, the same as the Palu tsunami in 2018. Always we have to do a lot of reading and trying to collect material, etc. So the first thing we did was to analyze the dark buoy records. Dark buoys are pressure sensors that are located in the middle of the Pacific Ocean in a very high depth. We are talking about 2 kilometers of water depth, something like 3 kilometers. Okay, from those records, we could see that actually the maximum were following the traditional belief that tsunamis were propagating over the ocean, but before we were getting these signals related with the atmospheric pressure wave, which is actually indicated here by green color. This is distant, this is time. In order to separate the nature of the analysis of the tsunami, in blue we have the Pacific Ocean station, and in red we have the Atlantic and Caribbean station, and also some in the Indian Ocean, for example, in Mauritius Island. Okay, the important thing here is that the traditional model, it was still kind of working, still showing the idea that you have a generation at the volcano, but still you needed a couple model in order to understand this generation of waves. So here is actually another plot, and here with Duncan, we were analyzing the non-dimensional numbers. First of all, we analyzed the fruit number. We noticed that we have a high fruit number. This fruit number is defined as the velocity of the pressure wave divided by the phase speed of a tsunami wave, which is a long wave, square root of GH. We will notice that that value was very high, and that implies that the pressure wave cannot have the capacity to create huge waves because it's too fast. It's too fast, the water, so he can react to that. The other thing that we notice is that we have a low Mach number. That means that every pressure change that we have above the water, we will fill it with the dark buoys, with the pressure record under the water. So we are perfect with that. The other thing that actually is still, I would say, still under debate is related with how are those waves. I think they are very long waves according to the measurements I have seen everywhere. What happens if those waves are too short? You will start to have dispersion effects, and that makes our life more difficult. Okay? Okay, so having those dimensional numbers with Duncan, we started to read papers from the past. And of course, the other big event related with the same nature is the 1883 Krakatoa tsunami. And actually here I have the most classic and the most popular papers, for example, Press and Hargreider, who were working with this idea of the generation of tsunami waves because of gravity acoustic waves. But also I wanted to highlight one very cool paper that actually is not very well known. And this is actually was a recommendation from Duncan, because Duncan has a huge memory of the study that people have done in geophysics. He's impressive. And he noticed this paper done by a postdoc, which is actually not so popular on that time. Now, I believe it's very popular because I have seen in many citations related with Tonga. And he was talking about the effects of the gradients of bathymetry and the water depth, amplifying the effect and the generation of tsunami waves because of the atmospheric pressure. And actually, he is right. Now that we have the coupled models, you can see those effects. So this is an animation that I did with my numerical model, which I'm trying to develop very well so everybody can use it. I will try to finish soon with that code so everybody can use that. But I want to show you here the explanation of how you can generate tsunami waves in a simple way. You have an initial condition, which is the classic source. And after I put play here, you will see an initial condition as well related with a LAMP wave, which is one of the modes of the acoustic gravity wave. And it's the dominant wave that it was coming from the volcano last year. So you will see that you start to propagate. Something happened there at the trench. And finally, you end up with, I would say, 3 waves. Let me put it here with the mark so people in Zoom can see it. You have 3 waves there. One wave is basically the classic mechanism from an initial condition at the center of the volcano. Another mode or another type of wave is also what we call the decoupled wave created by the atmospheric pressure. What happened? If you go back again, if you go back again, you can see that in the deep region, you are creating a wave. You are increasing the wave because basically you are changing the Fruit number in that area. This VP divided by square root of the H. But the thing is that you created that wave, but that wave anyway in this region cannot travel faster than at the same speed that the atmospheric wave. So therefore it has to left behind. So you will have a decoupled mode and you will have a coupled mode, which is a wave traveling with the LAMP wave, a tsunami wave traveling with the LAMP. So you will have these 3 types of waves. In the Atlantic, we are lucky because we have continents, and therefore we can clean and we can isolate the effect of the pressure mechanism generating tsunamis. You don't have the initial condition because you have a huge shield there, which are the continents. So this is very good. Okay, so using this animation, and basically that animation was written by something that I thought that year that it was very important because probably we will spend some years, many groups trying to understand and reproduce and try to understand more properties related with the volcanic tsunamis and these pressure mechanisms creating tsunamis in other oceans. So because of that, I created a new code, which I call the Supreme Concord, which is the tsunamigenic pressure model embedded in Concord, which is basically the classic Concord model, which was developed by my advisor, but I'm adding new modules in order to create the tsunami. So it's a coupled model. In every time step, I solve the LAMP wave equation, and after I solve that thing, I solve for the tsunami model. And of course, I need to modify the boundary conditions because now we need to model the complete planet. So therefore, I need to add periodic boundary conditions. I need to modify the input parameters, etc. It will be ready soon, I hope. First of all, I need to reproduce some things that I still cannot reproduce. Okay, this is the first try in a very large coarse grid. And probably you already saw this model in which you have the LAMP wave, the pressure wave, and here you have the corresponding tsunami wave generated by the pressure wave. And probably you notice this effect of a big wave created here in the Tonga Trench. Basically, this is the same mechanism of the trench that I was showing you before. And this is a very nice observation because probably what happened in some places of the Pacific Ocean is that actually that big wave that we are observing and which is actually consistent with the traditional mechanism is maybe actually a wave that was created here in the Tonga Trench, which is super close to the source. So basically a tsunami created in the Tonga Trench will have the same timing as the other one, as the traditional source created at the volcano. So probably we are just capturing pressure waves, pressure-induced tsunami waves. That is what maybe we're capturing. We're still under developing the model and try to find more things. But at least in terms of measurements with barometers around the world, this is records coming from the IRIS network, the seismic network, and comparing with dark buoys in the ocean, we are doing a very fair job. We are capturing the most important content. This is still an open question though, because I'm still suspecting that we have something interesting there. Okay, but the problem here also is that the waves, the tsunami waves created by a volcanic tsunami is actually, they seems to be shorter than the typical tsunami waves that we observe from earthquakes. What that means? That means that that wavelength will be closer to what you can find in coastlines, in bathymetry. And if you have a wave which has a wavelength comparable to the coastline, what will you produce? Edge waves and resonance. So probably, and one of the things that I haven't proved, and I need a method to solve that, is that probably volcanic tsunamis are more prompt to create resonance in some characteristic size of marinas and bays that we build in the coast. Okay, and this is two illustrations. This is Takoradi in Ghana, this is Punta Delgada in the Azores. And here you can see that there are very strong records of tsunami after the Tonga tsunami. Okay, so of course, I took my model, which is, by the way, have nested grids, and I tried to refine the resolution in the coast in order to reproduce this resonance and edge waves. This is actually not in the Atlantic. This is Chañaral in Chile. This port is very important because here we could find the maximum amplitude related with the tsunami of Tonga. The height, the tsunami height was almost 4 meters. You see, a huge tsunami. It is huge. We have to be careful with it. So what I want to show you is that here you are receiving now the wave coming from the Tonga Trench. And look at the harbor. You can see that you have amplification of waves. So something is going on with the local bathymetry. And you need to include that in your models. Otherwise, you cannot reproduce anything. For the Azores, it's even more notorious what I'm telling you. Let me try to move forward because we need to wait the way to come to cross the Pacific Ocean and all that stuff. Here we are arriving. Sorry. Oh, I got. Let me go back. Okay. This is Punta Delgada, and the measurement is here. The tide gauge is inside that marina. Take a look at that marina. What is that? Coastal resonance. Energy is getting accumulated inside that marina. Now, the problem is with my model that you have in red here, I cannot still capture the record of 1 meter, 1 meter and something. Why? I have some ideas. One thing that I'm testing right now in the computers at the office is a secondary mode that was which was created in the atmosphere, which is called the Pekeris mode. And that Pekeris mode is actually investigated in Japan, and some Japanese groups are actually finding very good agreement when they are including the Pekeris mode. What other thing can happen? Maybe I have to increase the grid. I have to make more resolution so I can prompt the generation of edge waves of the island, but it still cannot reproduce the same time. I'm still working on that. Okay. If let's imagine that tomorrow I finally solve and I can reproduce this event, then we need to jump to the next step. And the next step is to think, okay, what we will do with this instrument. Are we able to create a tool for tsunami hazard assessment for the future? Of course, the question is very open because we need to find recurrence of these explosive volcanic tsunamis. We need to identify what are the possible volcanoes which could create these huge things. So far, we only have had 2 events recorded, Krakatoa and Tonga, and we need to do something. Okay, some of the open questions I would like, which I think are important, first of all, are related with some uncertainty parameters in our model. For example, temperature defines the phase speed of that land wave. Probably if the eruption happened in summer, it will be different from what we had in January. Probably we will face some effects. We need to investigate. Also, as you saw, the trenches are very important. What happened with our uncertainties of the bathymetry? And actually, we were having a meeting with John Goff a couple of minutes ago related with how we can deal with the uncertainty of the bathymetry. Or maybe we can have to wait until 2030 once we can achieve the goal of mapping all the ocean, crossing the finger that can happen. We need to do that. We really need it. Okay, and the other thing I want to show you is that probably we need to improve our land wave model. This is measurements from Meteosat during the Tonga event, after the Tonga explosion. And this is actually the arrival of land waves arriving to the antipode. Actually, here you cannot notice very well, but this is Northern Africa, and here is Algeria. And in Algeria, you got the antipode of the volcano, where you're supposed to concentrate all the energy again. And another cool thing that probably you saw on Twitter, because someone did this thing before me, you can see the reflections in the Andean mountains. So we need to improve our land wave model propagation. And that is one of the things I'm doing right now. So hopefully I will have news soon. Okay, so as a conclusion, and here I finish, 55 minutes, that's very good. Basically, Tonga, it was a great opportunity because finally we have a lot of data to finally prove all the theories that people have developed in the past century after the 1883 event. Finally, we have data to prove things. Second, the role of land wave. Land wave certainly is important. Now I'm completely convinced. I was not convinced 5 days after the event, but it's important. And we need to consider that. And we need to know how to model those. And finally, of course, we discover the role of topography. As you can see in Chile, the role of the bathymetry, especially the local bathymetry, resonating these tsunami waves. And certainly we need to do more work in terms of uncertainty. And of course, we have still a lot of open questions. Okay, and this is what we are doing with Duncan, with Matthias, and I hope that in a couple of months I will be able to share with you the model so anyone can do a tsunami model and finally can try to find more solutions more than me. So, well, just acknowledging my students. I started last year at San Diego State, but I already found very cool people. This Andrew, for example, and Cameron are running some probabilistic tsunami hazard assessment in the California coast. They are learning super fast. At Scripps, we are working with GNSS antenna. Actually, now we submitted a paper in which we are measuring wind waves and sea level at the coast. We put an antenna here in the Scripps pier. So we are trying to develop that area because I think collection of data next to the coast is critical. We need to increase our data sets in the coast in order to have more observation and try to understand better the physics. And finally, also here is another application related with metro tsunamis, which are other type of tsunamis created by pressure disturbances in the atmosphere. Okay, so that's all. I hope you like it, and thank you for the invitation.
Ignacio, that was a great talk. Of course, we're going to entertain some questions. Constantino is already setting up the football, so because we have people following online, please use that to address a question to Ignacio.
Nice. Thanks. I can hear you, but not the rest.
I was like saying, it was an excellent talk. Excellent.
Thank you.
I have a ton of numerics questions that are definitely too niche to ask here. But I was wondering if there's a Freud number where you don't feel the bottom. I can imagine an ocean that is so deep that you would never feel it. And are you anywhere near that? And the other question, I do a lot of laboratory experiments, and this seems like something that would be reproducible in a lab that you could start changing some of these parameters to see what that, have you ever thought about working on labs?
Certainly. The thing is that in terms of numerics, there is a lot of things that I have been trying to solve. There is, for example, now that I'm changing to a global model, I'm experiencing the problem of the polar issue, which is basically trying to put a boundary, and probably I can change completely the scheme and I will get rid of that problem. But yeah, we are still working on that. For now, what I'm trying to do, at least from my side, is trying to come out with the leading order things. For example, the land wave. I know that with the land wave, we are having a problem with the timing in the Azores, or certainly there is something different that is coming here. So I guess with this kind of tools, we will be able to discover those things. Now, for the lab experiments, probably very soon we will need to define a way to try to do experiments and try to reproduce and try to understand much better how is the coupling between the gravity acoustic waves and the ocean. Because we are still dealing with formulas from the 50s, 40s. Because why? Because nobody was interested on this kind of thing. Now everybody is super interested. So certainly there is a lot of opportunities for improvement and to find more things. As I say, this is an open question still. I cannot reproduce everything. Yeah.
Any other questions?
Thank you so much.
Thank you.
Hi, that was a great talk. I was wondering about how the land wave decays when it goes around the Earth, and if you had like a really explosive eruption quite close to the US, would you have a bigger response in the coastal areas, or would any explosive eruption anywhere on the Earth could excite this response?
The land wave is pretty interesting, and I would tell you that in a couple of weeks we have discovered more about what's going on in terms of dissipation because of bottom friction. Probably not too much, but what really is very interesting, and you can see from the satellite measurements, is that probably you have a lot of scattering of the land wave. And also you may have other weather factors that are changing the shape, and probably you are changing directions, you are changing amplitudes, and even in some places you may have some constructive interference of the wave, and you will create more amplitude in some places rather than others. So in terms of propagation, the problem is complex, and certainly now we are working on that, trying to improve the land wave model. Yeah. So yeah, there is a lot to do on that side. Thank you.
Yes.
Hi, great talk. Just thinking about something fundamental that I thought was obviously important, the topography or the bathymetry when you're going on such a large scales and heterogeneity, and obviously you don't have the highest resolution of topography. So those uncertainties, how can you pinpoint them, translate them to the overall uncertainties? Do you have some constraint, or what's the highest resolution that you need in order to mitigate that? Because that seems to me the most critical component, either to inhibit the tsunami or kind of give it a...
Exactly. Very good question. And actually, this is one of the things we were thinking. When we were doing another problem, trying to work on another paper a couple of years ago, I was very interested on what was the effect of the uncertainty of the bathymetry into the tsunami behavior. And actually, the answer from the models that I developed, or I just ran with different sensitivity analysis, was kind of common sense, which is basically the tsunami will only feel or will only bother about features of the bathymetry which are comparable to the wavelength of the tsunami. So that means that probably the roughness and all this high wave number content that you are not capturing with the altimetry data and with the gravity method probably are not so important for the tsunami on those sides. And probably you will be fine as long as you can describe broadly how is your trench in terms in the wave in the length scales comparable to the tsunami wave. Probably. I'm not sure, but probably that will happen. Now, if you compare, for example, what happened at the dark buoys, you can see that the first leading wave is very well reproduced. So that can tell you that probably you have sufficient bathymetry in order to reproduce what is going on, at least in the near field of the Pacific Ocean. However, if you go to the coastline, then you have the problem that you need a very high resolution next to it. For the Azores, we were able to do that because we have very high resolution bathymetry in the Azores and in Punta Delgada, and we can describe that. We cannot do the same in Ghana, for example. In Takoradi, it would be impossible to do a reproduction because we don't have bathymetry. Someone can tell, oh, maybe you can apply an uncertainty model of the bathymetry and try to come up with something. But the coast is actually the worst place in order to try to even quantify an uncertainty because you have sediments, you have, it's very problematic.
Yeah, it's the worst, but it's the most critical zone. This
It's
is
the
what
most
affects
critical
humans, and this is what kind of determined the height of the tsunami eventually. It's like just like a surfing wave.
It's one of the most important parameters or variables that you need to include in the model. Right now, we are only able to try to reproduce the Tonga tsunami only in specific places where you have very good bathymetry. In the rest of the places, forget it. If I don't have data, for example, in Japan, in the coastal region in Japan, it would be impossible for me to try to build a model in Japan if I don't have that bathymetry. A bathymetry is everything. Every time when someone asks me if I can do a tsunami model of something, actually last week a friend was asking me because they have a lake in Chile, and actually Jamie was telling me yesterday that he did some exploration in the lake there in Chile. So a friend was super interested to try some tsunamis there. The first question, do you have bathymetry there? If you don't have bathymetry, forget it. You cannot do anything. Yeah.
Got a question. Luke in the back.
A very weird question for you. Pressure waves in the atmosphere can be generated by meteor impacts.
Yep.
Have you thought about looking at whether or not they cause like changes in the waves in the ocean, stuff like that?
And actually, the funny thing is that one time, a couple of years ago, I went to a session in AUU in which there was a session about tsunamis created by asteroids and spaceborne sources. And actually, the pressure is one of the most important components. Actually, pressure is responsible for a significant amount of tsunami amplitude, actually. Yeah. It's very important.
Yeah, so I was thinking, there's one big one that happened in Siberia not so long ago, and it happened in the middle of the continent. It would generate a pressure wave that would propagate across the planet. And you might see on the buoys some signal related to that stuff.
It would be super important, and certainly you can apply this model. But I would say that now, probably in the short future, people will start to improve our models related with these huge, large-scale atmospheric waves. If we can do that, probably we will start to have many models, and if we can reproduce this land wave and the different modes related with this eruption, probably we will have tools for asteroids. Yeah, but actually I was thinking on that. And in meteo tsunamis, I have those are the two applications I'm thinking about. Yeah.
Okay.
Yep.
Would you expect a land wave from tsunamis generated by a giant meteoritic impact?
I don't know. It can be a possibility.
Yeah.
Do you think?
I don't know. I'm thinking maybe there is an analogy between tsunamis from volcanoes and meteoritic impact, and maybe that this kind of wave or tsunamis could explain some geologic records we could actually see, across the whole planet.
Yep.
Thinking of this.
I think it's a possibility. It's a big, large-scale perturbation in your atmosphere.
Yeah.
And that you have restitutive forces, which is gravity, propulsibility. You need to propagate a wave. And certainly, yeah. Now, in terms of the way, as simple as this case, because here is very simple and the satellite images are illuminating that the wave is kind of well predicted, and the barometer are showing clearly the way. You don't have like super huge dispersion and other headache that you typically have in water. Here is like kind of simple. I always imagine that actually you can just come up with a vertically average model of this thing, and you can add everything and all the complexities maybe, and you can have a very good leading order approximation of this thing. And that is what we are doing now, actually. Yeah.
Have a question in the chat.
Yes, John Goff asks, great talk. Well, key comments first. Great talk, Ignacio. And then he asked if the pressure wave tsunami was amplified and left behind by the Tonga Trench, was there a second amplification of the Chile Trench?
Yeah, the thing is that we saw that because Matias always was thinking that the Chilean Trench was doing the magic. But certainly if you compare the model, the Tonga Trench is deeper, is closer. So the generation of the tsunami there in Tonga Trench is way much stronger than the one that we are creating in Chile. It's not only the depth, but also because you have a huge amplitude next to the source. Because basically you have this directional spreading of the azimuthal spreading of the wave. So the Tonga Trench is more important than the South American Trench, yeah, in terms of tsunami genesis. Yeah.
Any other questions? I have one too.
Yep.
So in all the probabilities that you're adding on and compounding in your calculations, some of the tsunami, of course, that we know have been generated by landslides, the large Alaska earthquake, even the 1937 Grand Banks earthquake. Is it at all possible to characterize that, or is that not a tractable problem?
That is a very good question. And actually, I was trying to write a proposal related with the problem of landslide tsunamis, because with landslide tsunamis, you have the big problem is that, okay, first of all, you have the uncertainty of the occurrence of the generator of the landslide. Let's say a big earthquake creating a strong ground shaking and prompting the failure and created the landslide. So first of all, you have the uncertainty of the source, and then you have the uncertainty that how you will trigger those landslides. And after you have those things very well known, then you can go with the tsunami modeling and all the simulations. I know that there are some relations that based on a ground shaking with a certain acceleration, you can come up with some distribution of the number of landslides you can create, and there are many studies, not only from the tsunami people, but more related with seismologists and people working in geotech. I think in the future, we will be able to do something better, but still we are in a very early stage in terms of trying to do a probabilistic tsunami hazard assessment related to landslide. It's not even included here.
And that's the limitations is the knowledge of for example, the continental margins, or is it a numerical problem too?
It's a problem related with the generation of the landslide, but also, as I was saying before, the problem of the headache, the wavelength of the tsunami created by landslide are very short. You have a lot of dispersion problems, and the models for a landslide tsunami probably are more complicated than the simple one with big sources. So there is a lot of challenges actually. For Palu, I'm always have believed that Palu was created by landslide. All the tsunamis that we have observed, and now we are even finding more videos showing that actually there is a landslide, there is a wave, there is a huge inundation. So there is many people that are still arguing that the super shear mechanism was creating things, but probably it can help, but landslides are kind of clear. So after that answer or that conclusion from our side, we were thinking, okay, how we can predict things for the future. And that is an open question as well. It's challenging to try to predict. And Palu, in a specific, Palu is a little sea harbor in Indonesia, where there was a huge tsunami in 2018. And the sediments are very poor, and the terrain is very prone to landslide everywhere. You have an earthquake and you have landslide everywhere, including, I believe, inside the water. So the problem is that if you have another earthquake, probably you will have more landslide. Maybe you have an earthquake tomorrow, and probably you will have another tsunami, just separated by 4 years. It's possible.
Well, let's thank Ignacio again. That was a great talk, great discussion, everybody. Thanks for coming.
Thank you for the invitation.